Uh-oh, I got the spinning beach ball before we started. I hope that's not an indication that this is going to stop in like 11 seconds, like it sometimes does. I think we've made it. Okay. Sometimes we want to evaluate a definite integral by interpreting it as an area. Okay, and of course, if we're going to interpret it as an area to find an exact value and not an approximate value, then the region has to be a recognizable shape for which we know a geometric formula. Okay, so that's what we're doing on example 10. It says to sketch the region corresponding to the definite integral, then evaluate the integral using a geometric formula. So in this case, we're basically using the area to find an integral. Using an area to find an integral instead of using an integral to find an area. Okay, so the integral from 1 to 3 of 4. In the next section, we'll learn how to do that using the fundamental theorem of calculus. But today, we're going to do it using geometry. So the graph of y equals 4 looks something like this. The y value, 4, and we're looking from x equals 1 to x equals 3. So because my graph is entirely non-negative on the region, and it's bounded by the x-axis, this will represent the area of the region, which of course we recognize as a rectangular rectangle. Good. And so the width is 2, and the height is 4, and it is not drawn to scale. But that's okay. So the area would be, and here's kind of a good, again, advice for free response type questions. If I showed a 2 down there and I showed a 4 right there, then don't just call that 8 on a free response, because remember, the free response is not just can you get the right answer, it's all about can you communicate how you arrived at your answer. And just by putting 2 times 4 there, you've done that. And so the answer is 8. Now, the other way to do it, preview of coming attractions. Preview of coming attractions. If you can find the antiderivative of 4 with respect to x, you can do it using the FDOC, the fundamental theorem of calculus. What's the antiderivative of 4 with respect to x? 4x. You wouldn't need the plus c, as we saw already, because it's going to cancel, and you would evaluate it from 1 to 3. That's how you would do it. And the way you evaluate it is you plug in the top minus plug in the bottom. So when you plug in the top, you get 4 times 3 is 12, minus plug in the bottom, you get 4 times 1 is 4. What's 12 minus 4? 8. But we don't know how to do that yet. Okay? So we're interpreting it as an area. All right. Sometimes you're going to prefer to do it by interpreting it as an area because the equation is either going to be really hard to come up with or very hard to anti-differentiate. All right, here we go. The integral from 0 to 3 of x minus 2. What's the graph of x minus 2 look like? That's right. A line. So the y-intercept of negative 2 and a slope of 1. So it looks something like that. And we're integrating from 0 to 3. So 0 is right here. I got that. Where's the x-intercept? Don't think too hard. 2. And so we're integrating to 3. All right, so we're looking for the integral. So notice that if I'm looking at it bounded by the x-axis, it forms 2 recognizable shapes, right? What are they? Triangles. Can we find the area of a triangle? Sure can. It's 1/2 the base times the height. So this is going to have a height of 2 and a width of 2. This one's going to have a width of 1 and a height of what? How do I find the y value there? It should just be the function value, right? So 3 minus 2 is 1. Okay, so here we go. Let me move this down so I can put my work right here. This is going to equal 1/2 the base times the height, which is 2 times 2, plus 1/2 the base times the height. Is that right? That's not right. This is where you have to be careful. Here you're using area to help you find the integral. We're integrating from left to right, so that's in chronological order. So anything that's below the x-axis is going to end up being negative accumulation, and it has to be negative. So if we're using the area, that's fine and dandy, but we have to make sure we're assigning it the correct SIGN sign. So that first term should rather be minus. Yeah. And if you want to include the minus, like in the height, because you're actually having a negative y value there of -2, that's fine. Just don't forget that sign. This is where you're using area to find integral. All right, so if you evaluate that, then you get -2 plus a half, which is -3/2 or -1.5. So again, it's not drawn to scale. The way I drew it, it almost looks like the positive region is greater than the negative region, which if they were true to size would be a net positive accumulation. But in this case, the numbers tell the true story, okay? So like any good old SAT question that's not drawn to scale, it could be misleading. All right? Easy enough? Number 6C, 10C, sorry. There's 6's in it. All right, so the square root of 36 minus x squared. That one, believe it or not, when we even know how to use the fundamental theorem, that one's not going to be very fun to find the antiderivative of. Yucky, yucky, gross, gross. I think you might have learned to do it in physics earlier in the year if you're in calculus. Do we still have calculus-based physics? No? Oh, this one showed up when they did calculus-based physics. It's not a very pretty antiderivative, so this is one where we might prefer to interpret it as a geometric area. What does the graph of this dude look like? Well, let's see. The equation would be y equals 36 minus x squared. That would be the function. If you squared both sides, you get y squared equals 36 minus x squared. If you add x squared to both sides, you get x squared plus y squared equals 36. That might be a more useful version. That's a circle centered at the origin with a radius of 6, okay? But because we solved it for y and we had the positive root, it's actually just going to be the top portion, the positive portion. So it's going to come out to -6, positive 6, positive 6, and it's going to look like this because it's a positive portion. So that could be like a new parent function that you recognize. If you have f of x equals the square root of r squared minus x squared, that's going to be a semicircle with a radius of r. Okay, so notice we're going from -6 to 6. Oh, well, I wrote it as r squared. Oh, yeah, sorry. Yeah, so it would be r. Yeah, if I wrote it as like big R, then it would be the square root. Yeah. Thank you. So all we need to do then, it's going to be positive, right? This will represent the area because we're going from left to right and it's above. So the radius is 6. So the integral should equal, what's the area of a circle? Pi r squared, and then we just divide it by 2, and the radius is 6. So there's your setup. It indicates your method. It ends up being half of 36, which is 18 pi would be the simplified answer. Could we use symmetry there to help us? What if you were lazy and you wanted to just find like the quarter circle? It could be 2 times the integral from 0 to 6 of that equation. Would that be helpful? I don't know. Sometimes symmetry is going to be helpful as you see. In this case, since we're interpreting it as just a semicircle, it's probably easier than thinking of it as a quarter circle doubled, right? But sometimes symmetry can be helpful. But it would be equivalent. Okay, and then the last one here. I'm going to let you do this one. I'll give you 2 minutes to do it. The integral from -1 to 4 of the absolute value of x over x. Find the integral using area. Don't just jump to conclusions thinking it's not possible. I would hate for you to jump through conclusions regarding the impossibility of its integrability. Remember, if a function is continuous, it is integrable. But sometimes we have functions that are not continuous that are still integrable. So I'd hate for you to jump to the conclusion that it wasn't. Open circles, open circles. La, 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 la. Hombre trefador? Yeah. Girl, I'm going all the way to the y-axis. Put like a big old, there we go. There we go, because it does go all the way up to it. Nice. Nice graph. Now you just got to work it. Work it. Yeah, no, that's right. That's right. LaTeX hat, ow, tough hag. Right. Any size will do. Any answers? Any answers? Oh, wow, you're doing a different one. Okay, carry on. Oh, doing the worksheet. Carry on. What is this example? No, this is the derivative of the absolute value vector. Actually, the graph itself is Jumpman. It's Jumpman. In my head, I haven't written it down. Haven't written it down? Yes, good. I see your right answer. That's good. Saving battery for another class, for a more worthy class. I appreciate it. Well? It was working. Did you charge it over the 3-day weekend? No, you didn't. Where's your WoW charger? Jumpman? Remember Jumpman? So he's coming in, it's 1, just like plug in a value like 3. 3 over 3 would be 1. Plug in like a 4 would be 5 over 5, which is 1. So it's 1 to the right, and then negative 1 to the left. Yep. Well, we're going on a non-symmetrical interval here. If we were going like from negative 1 to 1, it would be 0. But we're going from negative 1 and then all the way to 4. So the one rectangle is bigger than the other. Yes, good. Yeah. Yep, good. It's a good book. Yep. Log, did you get it? Yes, I think. Yeah, there it is. Perfect. This is absolute value of x. The graph that we have, this is the derivative of the absolute value of x. This is Senor Salta. This is Jumpman. Yeah, Jumpman. Okay, so remember, Jumpman is one of your parent functions that you have to recognize. Now you got to use the areas there. The absolute value of x over x, it could also be x over the absolute value of x. So if it were flipped, it would be the same function. And remember, it's undefined at 0. You have 0 over 0 at 0, which is the exclusion to the whole. This is the jump. And so when x is positive, you're going to have a positive 1. And when x is negative, you're going to get negative 1. And you could do that just by plugging in random values. 5 over 5, 7 over 7, negative 7 over negative 7. Of course, the top becomes positive, so you get a negative 1. Now, we're integrating from negative 1, which is there, to 4, which is there. So I'll try to draw this one a little bit more to scale. So we basically have 2 rectangles, or technically, I guess, a square and a rectangle. And we're in charge of assigning the correct values. So we're integrating from left to right, which is chronological order. So the region below is going to be assigned a negative value. Bless you. And the area is going to be 1 by 1. So I'll do it like this. Now you can go negative 1 times 1 if you want to do something like that. Plus the next one is going to be a rectangle that's above, so it'll be positive. The width is 4, the height is 1, so it'll be plus 4 times 1. And of course, on a free response, you could stop right there, but it ends up being negative 1 plus 4, also known as 3. So even though there is a discontinuity there, the function doesn't exist, because we could see where those y values are going, it doesn't inhibit us from finding the area. It's essentially the limit. The area is the limit of those as it approaches, it gets closer and closer to 3. So the area, we can actually say, is 3. So some functions that are not continuous are not differentiable, as we'll see when we get to improper integrals, but sometimes they are. And holes and jumps technically or typically don't interfere with finding area. Okay, any questions on those? Using area to find integrals. This is another one where we're not going to really want to do it using the fundamental theorem of calculus, finding the antiderivative. what would the antiderivative of that be? Some of y'all were actually graphing it. Yeah, it's the absolute value of x. The derivative of the absolute value of x is Jumpman, and Jumpman's antiderivative is the absolute value of x. We would need the plus c. So if you evaluated that from -1 to 4, I think you'd get the same thing. You get 4 minus the absolute value of -1, which is 1. You do get 3. So it does work out, but you'd have to like memorize that antiderivative, which isn't bad. Okay, Here we go. Example 11. This graph right here was on an AP exam, I believe in 2000 and something. I forgot. 6, 10, I don't know. But it was the last question on the exam, and a lot of people got fatigued because it was a test where like 5 of the 6 pre-response questions dealt with integrals and accumulation on intervals. And this one was the last one, and it didn't have any units. All the others before this were contextual, like we were accumulating raw sewage and speeds and stuff like that. This one was just a graph. And so I don't know if it was fatigue or what, but a lot of students did poorly on this, and I thought it was actually one of the easier ones. So whatever the reason, let's look at it. I've kind of modified the question, but I've used the same graph. It says the graph is a function y equals f of x. It's composed of 3 line segments in a semicircle. Okay, so line, I see that, line, line. And this shape here, which appears to be a semicircle, is in fact a semicircle. Got it. Part A, evaluate the integral from -7 to 0. Okay, part A. Evaluate the integral from -7 to 0, f of x dx. So here's another time where we're going to be using not area approximations, but actual areas to help us evaluate an integral. So -7's over here, and 0's right here. So if you notice, it's made up of a triangle and a what fraction of a circle? Quarter circle, all right? So the radius of the circle, just to be careful, is what? 2. And then the width of this from 2 to 7 is 5, and the height is 1. So not a bad idea to label your dimensions there, and then again show them in your calculations, indicating your method. Okay, so we're going from -7 to 0. That's left to right. So everything is as it appears. Negative y values are going to be negative accumulations. Positive y values are positive accumulations. So the first one is going to be what? Positive or negative? Negative. Get that sign out of the way. Negative. Now it's a triangle, so 1/2 the base, which is 5, times the height. Done. The next one from left to right is above, so it's going to be a positive region. And it's a quarter of a circle, so it's pi r squared and then divided by 4, and the radius is 2. Now, this was a free response question. Is that a numeric answer? Does it indicate your method? Yeah, you walk away. It's done, okay? It's pristine, it's perfect. I'm going to keep going at this point just to show you that it can be done. 4/4 is 1. You get that. So it doesn't even turn out to be really that pretty. Pi minus 5/2. Yeah, if you do it like that. No bonus points for simplifying. Yes, Schroeder. Oh, okay. You don't need to apologize. All right. Pretty easy, right? Part B. It's asking us to integrate from 2 to 5. 2 to 5. 2 to 5. Okay, so come down here. Keeping the graph in sight, the integral from 2 to 5. Oops. And this is part B. Okay, so 2 to 5. That's going to be, use a different color here. 2 is right here, and 5 is right there. 2 to 5. Okay, so it looks like we're going to be, whoa, I got a triangle. I see the triangle, and it's from left to right, so that should be positive. And then I have a little triangle down here that's a right triangle. That'll be negative. I think the height of this triangle I can easily determine is 3. I think the height of this one I can easily determine is 1. But notice there's something that's a little bit awry here. This is not intersecting the x-axis at a nice integer value. So I need to figure out the point of intersection right there. Where does it cross the x-axis? Do you just want to assume it's halfway? It was last year. That's funny. No, we don't want to assume it's 4.5. Because what if it's 4.6? Then we're wrong, right? So let's quickly determine what the X-intercept is. How do we do that? Well, to do it quickly, you would need to write an equation of the line very quickly, which you could do, right? We have 2 points. What's the slope of the line? You could say, okay, what are you rising and running? You're going from y equals 3 down to -1. So that's falling 4 units. And you're going from 3 to 5, so that's running 2. So the slope should be -2. And then you could choose your favorite point. I'm going to choose 3, 3. So the equation of that line segment would be, in Taylor form, y equals the y value 3 plus the slope, which is -2 times x minus 3. And now to figure out the X-intercept, how do you find the X-intercept of any function? Set y equal to 0. So again, signaling our attention, the X-intercept, we get 0 equals, I'll distribute now 3 minus 2x plus 6. So that becomes a 9, which when I bring across becomes -9 equals -2x. And x equals 9/2, which is what, Schroeder? 4.5. Okay, so now we know for a fact it's 4.5 and we're not just guessing. It was the same as last year. All right, so the width of this triangle down here from 2 to 2.5 then is 2.5. If you assumed it was 4.5, yeah. Yeah. And I'm actually surprised they made it 4.5 and not like 4.6. Okay? So look for them to do that in the future to try and bait you. And then this one here is going to be, actually, I'm not sure. I would like to say yes, but I don't know for sure because I didn't grade this problem. Perhaps not. Perhaps not. I would think that it would need to come out of somewhere. Yeah. All right. So from 4.5 to 5, that's a half unit, or write it as a ratio. Okay. So now that I have that there, I have all my dimensions kind of labeled. Here we go. The first one is going to be 1/2 the base, and the base is 2.5. I'm going to go ahead and write it as 9/2, and the height is 3. Okay. And then the next little triangle, is it plus or minus? Minus 1/2 the base, which is 0.5, or another half, times the height, which is 1. All right, so there you go. We had to find a little X-intercept, and we're done. On a free response, that's numeric, indicates the method. If we keep going, we get 27/4 minus 1/4, which ends up being 26/4, also known as 13/2. But 13/2 gets just as much credit as the first red line up there. And you can only possibly lose points if you proceed and make a careless mistake. Okay, so that made it a little bit interesting. The next thing, the follow-up question, do these integrals that we came up with represent the areas of the region? Why or why not? No. These cannot represent areas. Since what? Each integral, you could say the word spans if you want. Spans negative y values, something like that. Or we integrate over an interval that contains negative y values, or something like that. The graph lives below the x-axis in each of those intervals, okay? So they can't represent areas. All right, that's it. If you understand that, that was kind of the first part of the question. I think the X-intercept right here maybe threw some people for a loop at the end of a test, you know. The fact that it's not contextual, you're not really assigning any units or anything to it. Because once we get to Chapter 6, units are going to be in every problem, and everything's going to start having a meaning. Right now, we're just kind of accumulating y values that don't really represent anything. Okay, very quickly, a summary of the properties of integrals. Some interesting things. If we integrate from a to a, guess what the integral is? 0. Yeah, you could think of it as net accumulation. If you try to accumulate something from time equals 5 seconds to time equals 5 seconds, have you let any time go by? No. So you haven't accumulated anything because you have no interval of time. If you think about it as area under the curve, then the width would be 0, right? Going from A to A. So if you don't go anywhere, you don't accomplish anything. You don't accumulate anything. The next one we've already summarized, but here it is in the chart. The integral from A to B, it's the opposite of the integral from B to A. So if you ever need to make a region the opposite sign, you can either flip the intervals of integration or you can put a negative sign out front. And we could have done that up here. We could have rewritten it, but we didn't need to. We did it with our numbers. This right here, we saw this up above. This is the integral of a constant. It ends up being the constant times the width b minus a. Okay, if you have a constant that looks like this, and you're integrating from a to b, then it's going to end up being the constant, which is the height, and of course the width is just b minus a. So it's width times height. That also is going to come out of the fundamental theorem in the next section. If you're finding an antiderivative of separate terms, whether they're added or subtracted, you can give each term their own integral, which is nice. Just like we can with the derivative. They do get their own dx, which is the right bookend. You can kind of focus on each term separately and then combine your results at the end. This is the one that's going to be important when we move forward with integration techniques. If you have a constant multiple there, you're going to pull him out front. He's there in the beginning. He's going to be there in the end. He's just going along for the ride. He's in the back of the truck. He has no idea what's going on. He doesn't influence the problem at all. And then this one here is your additive interval property. If you're integrating from A to B, you can pick this arbitrary value of C, which we saw doesn't even have to be in the interior, integrate from A to C, pick up plus C to B. That's important that these two coincide through a plus sign. Okay, that's important because you have to pick up right where you left off and add the two together. And then the sign of the integral will make it all work out. I call these the additive interval properties. I also call them travel agent problems, as you'll see here, because you kind of sometimes have to make a connecting flight when you're flying from A to B, right? And if you fly from A to C, you better hope there's a plane at C that takes you to your destination, right? You don't want to fly from A to C and then have to fly from B to D or whatever, because how do you get from C to B? It doesn't work. Hey, speaking of travel agent problem, here's a good travel agent problem, right? We have to try and make this itinerary work. So if the integral from 0 to 10 of some function is 17, and the integral from 0 to 8 of the same function is 12, I claim that we can evaluate the integral from 8 to 10 of this modified function, 3f plus 2. Okay, so to do a problem like this, you want to think about what's given. Think of this as being like a two-way flight. We have information about going from 0 to 10. Okay, you can fly from 0 to 10, and of course we know we can also fly from 10 to 0, can't we? If I had to fly from 10 to 0, what would it be? Not 17, but negative 17, right? When you flip the intervals of integration, it changes the sign of the integral. So think of it as a two-way flight. Same thing here. You can fly from 0 to 8 and get positive 12, or you could fly from 8 to 0 if you needed to, and it would give you negative 12, the opposite. So, and you don't even have to write those down. You could just think about it. It's a two-way flight. Just change the sign if you have to fly the other way. So the goal is then to rewrite this in terms of f of x using 0 as the middleman, right? We're trying to go from 8 to 10. They both have in common 0. All right, so step 1 is to use the properties of integrals from above. I'm going to pull the 3 out front. I'm going to write that from 8 to 10 of f of x dx. And then the plus 2, I'm going to give it its own separate integral, the integral from 8 to 10 of 2 dx. That would be step 1. You're trying to isolate this piece right here because that's what you have to use the given information for. The second part is not going to be a problem. I can integrate any constant. pretty easily. In fact, let's do that on the next line. Okay, so on the first term, though, that's where the travel agent comes in. I need to go into my travel agent and say, look, I would like to fly out of 8 and arrive at destination 10. And the travel agent's like, okay, well, we don't have any direct flights that go from 8 to 10, but we do have a flight that goes from 0 to 10 and 10 to 0, and one from 0 to 8 and 8 to 0, so we're going to have to get you a connecting flight. So here's what you would do. You're playing the travel agent. You're going to have to fly from 8 to 0. You're not even worried about what the values are at this moment. You're just creating an itinerary. You got to start at 8. We're going to start at 8. We know 0 has to be our middleman connecting flight, so we're going to start at 0, plus then we're going to pick up at 0 and fly to 10. Okay, so no big deal. You got a connecting flight, a little bit cheaper maybe. I don't know. You get to pick up a souvenir pen in the connecting flight and say that you've been to that city. Whatever. So that takes care of this. And notice it's in beefy brackets, and I got a 3 out front because it was times the entire integral. Now this one here, we can go ahead and evaluate it because that's just going to be a constant, right? And if, again, you want to think about it geometrically, it's just the horizontal line, y equals 2, and we're integrating from 8 to 10. So that's going to be a width of 2 and a height of 2. So remember, it's just the y value times b minus a, which is the width. This is your height times the width. It's just a rectangle. So if you have like plus a constant, it's not going to be a big deal. All right, now, how are we going to evaluate the things in the brackets? This is where you return to the information. And I'm just going to say that I didn't write this stuff in red, because you don't need to write this stuff in red. You can just think about it. We have these two pieces of information. We know if we have to flip the intervals of integration, we'll just change the sign. All right, I need to fly from 8 to 0. Well, if 0 to 8 is positive 12, then 8 to 0 would be negative 12. And I'll just write it as negative 12. Plus, what's the integral from 0 to 10? Well, that one's given. 0 to 10 is 17. I'll write it like that. And then plus, I'll just evaluate this over here. 2 times 2 is 4. Is that numeric? Yep. So we're walking away. And then we're going to keep going because we trained for both, right? 17 minus 12 is 5. 5 times 3 is 15 plus 9 is 19. There you go. Travel agent problems. It's all about isolating the integral of f of x, pulling constant multiples out front, splitting it up with the additive interval property. Make sure you have your parentheses if any numbers out front. And then anything that's just added, that's just a vertical shift. That's just taking the graph and creating like a little platform, a little rectangular block of platforms for the previous graph to sit on if you want to think about what it's doing graphically. Okay, these make excellent multiple choice questions, by the way. And you can go practice those in your notes or your worksheet.
There is a blood drive happening tomorrow. If you are interested in signing up, please go to room 318 today to do that.
Using area. Okay. All right.
Channel 4 for the morning announcements. You can also view them online at abhstv.com.
All right. I guess we'll finish this tomorrow, but we got example 13 I still want to squeeze in here. Using area, again, to evaluate an integral is very helpful, especially in cases where maybe, like I said, you can't find the antiderivative or sometimes necessarily the equation if you're given the graph. This graph, I'm not sure what it looks like, but if it tells me to use the area to help me evaluate the integral, I'm guessing it simplifies. Now, here's some observations. If I just look at the function, f of x equals 9 minus x squared over x minus 3, I'm noticing that x cannot equal 3. Are you noticing that? And notice my integral is spanning that discontinuity. I'm going from negative 5 to 6, so I'm integrating through a discontinuity. Is that possible? Possibly, yes. It is possible. What type of discontinuity is it? That's going to be revealing. Is it a hole or a VA? It's a hole, because when you plug it into the top, you get 0. So remember, 0 over 0 is your hole, which is your removable discontinuity. So remember, if I want to know where the value of the hole is, I would factor. So let's go ahead and factor out a negative from the numerator, and that makes it x squared minus 9. Hold that in your head. It changes both signs. And then x squared minus 9 factors into x minus 3 x plus 3. Are you okay with that? Factor out the negative, change the sign, it becomes the difference of squares. X minus 3 divides out. And then the fun part. Those divide out, and you're left with negative quantity x plus 3, also known as negative x minus 3. So what this graph looks like is it has a, it looks like a line with a slope of negative 1 and a y-intercept of negative 3, but it has a hole at the coordinate 3, comma, what? Remember, all you have to do to find the limit is just plug it back into what's left. Negative 3, when you plug it in for x, gives you negative 3 minus 3, which is negative 6. Okay? Are holes going to be a problem when we find area or integrate? No. You saw jumps aren't either. Okay, so that can help us evaluate it. Let's go ahead and sketch the graph then. Negative 3 is down here, and the slope is negative 1. So it looks like that. And we're integrating from negative 5. So if we go from negative 5, that's going to end up being right about here. Because when you plug that into that function, negative 5, when you plug it in, gives you a 2. So that's going to be 2. Here's the x-intercept at negative 3. And then we're cruising all the way to 6, which will be about right here. If you plug that in, you get negative 9 for the height. So notice we have a rectangle that's positive because we're going from left to right, and a much bigger rectangle that's going to be a negative region. And of course, if you want to draw it true to scale, maybe somewhere in here you put an open circle. So now the hard part's done. We've identified the region. We know where the x-intercepts are. We know how to find the height by plugging it into this residual function, negative x minus 3. Here we go. We can now bring it back into the integral. And notice I was just calling it f of x off to the side so that I wouldn't have the burden of doing all that simplifying with the bookends there, with the integral and the dx. Okay, so now this is going to equal, the first triangle from left to right is positive, so 1/2. The base is what? From negative 5 to negative 3 is 2. And the height is the function value negative 5, which is 2. And then the next triangle is going to be positive or negative? Negative, because it's below. And then what's the width? From negative 3 to 6 would be 9. So it's 1/2, 9 times the height, which is also 9. The y value at 6. And then to finish it off, we get 2 minus 81/2. No bonus points for that. So that would be negative 70. That would be 477/2. Ugh. Yeah. Is it reasonable that we're going to end up with a negative number for our integral? Yep. Because this one is not really drawn to scale, but it's relative to scale. This region is going to be much bigger. Okay, there we go. We'll stop here for the day so that the worksheet's not due tomorrow. That's why we'll stop here. There's some interesting symmetry that we're going to look at tomorrow with example 14, and then we're going to roll right into the next section, which I think you'll like. It's going to be pretty easy because that's really the shortcut rule, the one that we technically don't know but we've already seen. Schroeder knows. It's going to be the same as last year. Okay. Quiz tomorrow, too. Real quick quiz tomorrow on those numeric methods. So be ready for that. Should be a lot of fun.